we go. You know, does not like. I believe we ended with here. All right. So in identifying a stereogenic center, people get a little bit confused about how we use that word stereogenic center. Basically what I'm referring to is any site that you can give a configuration to it. So you can assign it an R and S designation, or you can assign it an E or Z designation. They're both considered stereocenters. But specifically though, a chiral center is referring to the kind of carbons that we have here. So in order to have a chiral carbon, you must have 4 different groups coming off. And I just want to emphasize that we are going to be going by the first point of difference. The thing is though that you look at the group as a whole. If they are different groups coming off as a whole, then they are considered different groups. So what I mean by that is here we're looking at this carbon that's kind of being zoomed in on the bottom of the page here. And if you go one atom out, they're the same, next atom out, they're the same, and then you eventually do find a difference. So if you have a case where all 4 groups are different, that is a chiral center. It is also a stereocenter. So it's just like tomato, tomato, you know how you want to word it. Go ahead.
So Professor, if that group, for example, if both of the ones coming out the CH stereo, that, if they were both like ethyls.
Yeah, so here we have ethyl versus propyl. If there are both ethyls, then it's not a stereocenter.
Cool.
Because then you have symmetry. If you have an internal symmetry, then you can't have any chirality there. So if you had 2 ethyls there, that is equivalent to having 2 H's coming off. There's 2 of the same group. And the problem with that is if they're the same group, we can't give a priority to one over the other. So we have to assign priorities here. So, and first starting off with this, we do being able to identify stereocenters is a skill that you need to have, and then you also need to be able to assign them an R and S designation. So here we have a few examples here where the carbons with the asterisk on it is the chiral centers, and they could be drawn with a handedness to them. This particular compound does have them all just flat, but we could draw them 3-dimensionally and see that we do have a handedness to it. I do also want to mention here at the end we have sugars here. It turns out that in sugars, almost every carbon is a chiral center in a sugar molecule. They are highly handed, and you guys probably heard about the D and L sugars. They're actually referring to the handedness of it by having the D and L designations. And we'll probably get to that today, maybe. We'll see. All right, so this particular example here is how many stereocenters do we have? So basically any carbon that has 4 different groups coming off is a stereocenter. So what do you guys think in the first one? How many?
2.
There's 2. Yep, that one's really obvious. There are 2 of them. So here and here. And you guys remember the equation from the lab that we used to figure out how many total possible there are?
2 to the n power of n.
So it's 2 to the power of n. So the way that works out is the number 2 is the number of possible outcomes, and then n is the amount of instances of it in the molecule. So if you think about it, if you only had 1 stereocenter, the only 2 possibilities would be R or S. The thing is that when you start having multiple of them, that's how we figure it out. So once again, the 2 is how many possible outcomes there are. So it could be R, S, or it could be E or Z. And then the n is the number of occurrences. So if this had a double bond in there where we have E or Z as possibilities there, we have to include that in the total number of stereocenters when we're doing that 2 to the n calculation. All right, so next one here, I believe there's only 3 in there, and I do want to point out that the one on the far left, where we have that isopropyl group, sometimes people will confuse those as a group. The thing is, though, we have 2 methyl groups coming off that far left carbon there. So that is not a stereocenter. So how many possible isomers would there be of the bottom molecule? 8 possible, yep, 2 to the 3. So you think about it, it's all the different possible combinations of R and S that you could have. You could have RRR, SSS, RSR, and then all different iterations of that. And it works out that there are 8 of them. Okay, so in assigning R and S designations, what you want to do is assign a priority to the atoms by a first point of difference. So essentially you want to go out 1 atom at a time until something is different. And this first example here, we see that going one atom out, so we're looking at the bottom orders here. You were kind of given the orders already here. But the first thing, we go one atom at a time. It's going to work out where hetero atoms are priority. I'd say 99% of the time, because they all have a higher atomic number than carbon does. They're all to the right of carbon. So oxygen gets priority over carbon does. Hydrogens are always going to be your low priority because they are the lightest molecule, or sorry, the lightest atom on the periodic table. They're atom 1. Typically the hard part in designations here is groups 2 and 3, and that's usually where students get messed up. But the thing is, if you get those backwards, you're going to end up getting the backward designation. So the first point of difference here, so we go by the first carbon here, okay, they're the same. And then you look at what that carbon is attached to make a difference. So the first carbon that's attached here, this one has 2 H's and then a carbon, where this one has just 3 H's. That extra carbon bond is the tiebreaker. So you basically keep going one atom at a time until you can do a tie break, basically. All right. So here, once again, you want to look at it from the perspective such that the H is away from the view, and then you trace them from high priority to low priority. And which relative direction they go tells you whether it's R or S, basically if it's right hand or left hand. If it goes clockwise, it's what? R. Yeah, it's going towards the right, it's R, that's how I remembered it. And then if it's going counterclockwise, it's S. Yep, or sinister, but it's kind of silly, but yeah, it was for sinister. Technically, when you're doing these, you are technically looking at the Newman projection from the carbon to the low priority group. This will come into play. We do have some situations today that I wanted to work through where we have the low priority in the plane of the paper. That's typically when you want to do it from the Newman projection approach. So let me just go ahead and switch over to some paper here, and we'll go ahead and do some examples. Huzzah! Here we go. All right, so here we go, and let's do some examples. We'll go ahead and start off simple first, and then we'll just step it up from here. It's probably as simple as it's going to get. All right, let me turn off auto zoom and do a manual zoom. Sorry, manual focus. There we go. Okay. You want to get to the point with this material where looking at a simple compound, you guys can designate R and S like just by looking at it. You don't want to have to work through it every single time. But I can go ahead and work through this and the ones today, but just thinking about moving forward, you want to get really quick at these. Okay, so I am seeing one stereo center. So if you're being asked for the possibilities, remember it is 2 to the n is the number of possibilities, so there would be 2 possible, an R or an S. But that's not what the question is asking us. I want to go ahead and do designations. So you look at the first atom coming off and look for a point of difference. This one here has priority 1. It's the hetero atom. And then looking here, we have a carbon and a carbon, so then we have to go look at what that carbon is attached to. In this case, it should be pretty obvious. It's going towards the right is priority 2. And then going towards the left is priority 3. And if it is implied that the H is back in this case, so then you just trace the arrow from high priority to low priority. It goes like that, and that is an R designation. Okay, let's go ahead and put that in red, R. Okay. Sometimes you may be asked to draw mirror images of these, and there are 2 ways you can do this, and you'll still be correct. One is to actually draw a mirror of it, just basically flip this image, and sometimes people will actually put like a little line here to denote a mirror, and put this. And the key here is make sure the carbon is actually a mirror of it, and then looks like 3 atoms away from the mirror is where the chiral center is at, like that. And if you did this correctly, you should get the exact opposite designation. So let's go ahead and just 1, 2, 3. It looks like it's going backwards compared to the starting one. It's going like that. So this is a S designation. In my opinion, the easier way to do this is to just go ahead and draw out the normal version of it, the way that the original drawing was, and turn any wedges to dashes. And then you have the mirror image, like that. So if you think about it here, if we were to rotate this molecule 180 degrees, it would actually be this exact thing right here. To check if you're right, we can still go ahead and do our designations. So it's going to work out the same way here, where this is 1, 2, 3. Notice here now that the implied H is coming towards us. So you're actually looking at it backwards now. And I've seen textbooks do this the hard way, but I am a fan of the easy way. So the hard way is to like rotate groups around, change the way they're bonded together to get the answer. But literally what you want to do here is go ahead and assign the designation like normal. But if the H is towards you, you give it the opposite designation. So here I am seeing that it is going clockwise, but we're looking at the back of it. So it is backwards. So that is still a, what is it, RS? This one. S. And I like to do this silly little thing here to show you why we give it the backward designation. So which way am I turning my arm right now? Clockwise, and what would you give that? You would give it an R, right? Mm-hmm. But if you're looking at the back, see how it flips? Mm-hmm. That's what's happening here. So all you got to do is just give it the designation like you normally would, and then just flip it in the answer. All right? So what I want to go ahead and do now is look at a more complex molecule that have more than one chiral center. But before we do that, how are these related? Again, what was that word? Yep, enantiomer. Enantiomer. And these are your mirror images. And are they superimposable or non-superimposable? Yep, they're non-superimposable. And it's imposable, not impossible. Okay, so what if they are superimposable? What does that mean? If they are superimposable, it means they're not enantiomers. They are identical. An interesting thing too is that if you think about it, if you were to say you had a compound that had no stereocenters in it, and you're being asked the number of possible isomers of it, there should only be one, right? Because there's no R and S to it, and it does work out. If n is equal to 0, you have 2 to the 0. Anything raised to the 0 is equal to 1. So it does work out in the math too, where if you have no chiral centers, no geometric centers either, then it ends up being where there's only one, which makes sense. All right, let's go ahead and take a look at a different example now. This is a very classic example, and it'll be 2,3-dibromobutane. Very classic example here. And what I'm going to do here is I'm going to go ahead and draw the molecule flat, and then we're going to identify how many chiral centers there are, and then from there I want to draw all the possible stereoisomers and then make relationships between them. How are they related? So drawing this flat, we just have the butane there, and then we got a Br and a Br, like that, at carbons 2 and 3. And doing a problem like this, you just start anywhere. So I'm just going to go ahead and start with the way this one looks. Just go ahead and put wedges on it to give it some dimension. Now we can have some handedness to it. Okay, we have that. And then if I want to do the mirror image of this, I'm doing the mirror images here, so that, like that. And since we're just doing the flipping mirror image here, the numbering is different. So if this is carbon 2, then this is carbon 2. So just to be clear about the numbering here, this would be carbon 1, this would be carbon 1 over there. All right, but I don't want to confuse with all the numbering in here because I do want to do some numbering for priorities. Or we can probably do without numbering. This one here, what is it? So how many chiral centers do we have? 2. So I know that there's going to be how many possibilities then? 4 possibilities. 2 to the 2 is 4. Okay, which isomer did I just draw here? Is it RS, SR, SS? Are they both R? Yes, they are both R. So the way this works out is priority 1 is going to be the heteroatom. Going towards this part of the chain is priority 2. And the reason why is because, you go one atom out, they're both carbon, but this carbon has bonds to other stuff, where this one just bonds to H. So this is priority 2. So it's going 1, 2, 3. It's going clockwise, and then that makes it R. This one here, it's the same kind of thing. We have bromine is priority 1. Towards the rest of the chain here is priority 2. And then that's priority 3. So this is going clockwise as well. So this is RR. Okay. Without even doing anything, if you draw the enantiomer correctly, you automatically have SS. And that's just by the definition. The mirror image is the opposite designation. So without doing anything here, I know this is SS. As you're learning this stuff, though, I recommend that you actually make sure that it's SS to see that you're doing it correctly. So let's start at carbon number 2 here. So it goes 1, 2, 3. Counterclockwise, we're good. That is S. And this one goes 1, 2, 3. Counterclockwise as well. That is also S. And just for the sake of consistency here, if you wanted to do the mirror image the easier way, you just copy the way that the original structure looks, and then you change wedges to dashes. So that's another way to do it. That is also your SS enantiomer. Okay. All right, going downward. What I'm going to do here now is I am going to leave one of them the same, but change the other one. So I'm going to arbitrarily choose to change or to leave this one the same, the one at carbon 2, but the one at carbon 3 was flipped. So in comparing these two, I automatically know this is going to be RS. So the reason why I know that is because I left this one the same. So by leaving it the same, we did not change any designations. This one I flipped it by flipping the wedge and the dash. It is now S. We can confirm that by going, okay, it's 1, 2, 3. Did it freeze? I think it froze. There we go. It didn't freeze. It unfroze. It's going 1, 2, 3. It's going clockwise, but we're looking at the back, so it's actually S. Okay. Looking at these two now, are these mirror images of each other? They're not quite mirror images. And if they're not quite mirror images, but they still have the same kind of structure here, they are what? You guys remember from the lab? They are diastereomers. Yep. So diastereomers. And these are non-superimposable, non-mirror images. So they're not quite a mirror image, they're not quite superimposable, but they are still stereoisomers of each other because they have the same connectivity, that is different in three-dimensional space. All right, so I want to go ahead and do the mirror image here of the bottom one. So get that. All right. So just like you saw with the last one here, I automatically know what the designation is going to be. If it's RS, this is going to be SR because we just did the mirror image of it. So this should be R, this should be S. All right, so that we're clear here for each other. These two here, these are enantiomers. So I'm going to put enant for short. Going up and down on both sets here, these are diastereomers. I'm going to put the word abbreviation dia for short. And then it also works out going along the diagonals is also, how are those related? On the diagonals, they're diastereomers as well. So dia. And then the fun part of the question is, how are these related? They are actually identical. So here we have a situation. It turns out that if you have a situation where you have more than one chiral center, the molecule can be symmetrical overall. If you have a situation where if you have, yes, we do have handedness in there, but we have an internal mirror plane, that molecule is not chiral. So its mirror image is identical. And I actually brought some models here to show you what's going on. All right, I actually need to flip these real quick. All right, let's do some models. You guys love these things, right? Awesome stuff. All right, I believe I have the left one right here. And I want to go ahead and make the mirror image now. Let me raise this a little bit so it's not so close to the camera. There we go. And I now want the mirror image here. So this is not quite the mirror image. It looks like I need to flip this group. Like this. All right, so we have that portion. And then I believe this other portion is the same. So they are now mirror images. Do you guys see that? All right, so it turns out that we had an RS situation happening here. That should actually be the giveaway. So if you ever have a problem where you have the opposite designation within the same molecule, you want to start considering the possibility that the whole thing might be symmetrical. And here we do have an RS situation happening, and you can see if you rotate like that, and then the other one was the mirror image, I'm going to also rotate it like that as well. And what do we have now? They are identical. So in that situation where we have an internal plane of symmetry, the molecules are referred to as being meso. Yep, M-E-S-O. So these two right here on the bottom, they are actually identical. All right. And I do want to point out here that there are technically only 3 stereoisomers here because 2 of them are the same. And just keep in mind that your 2 to the n formula does not account for meso. We're just doing a probability thing there. So it does not account for meso, so you're going to have to take that into your own account.
So would you want us to say we have 2 stereo centers? When we calculate, you want us to do 3 instead of 4?
If the question is asking you to how many stereoisomers there are, you're going to have 1 less if you have a meso situation.
Subtract 1.
Yeah, subtract 1. Yeah, so here we have an internal plane of symmetry. And these are achiral. They do not rotate plane polarized light, and its mirror image is identical. The common example I like to think of when thinking of some real-world objects that are meso. So I did talk a lot about last time about how we have numerous chiral pairs in our body, like our hands and our feet, for example. You also have like your shoulders, your knees, your face has a bunch of symmetry in it too. But it turns out though that if you look at yourself in the mirror, you see an exact copy of you, right? You know, ignoring anything like scars, birthmarks, tattoos, that kind of thing. But your body is meso because you have a plane of symmetry right down the middle, on the outside. So things like the human body are meso, things like molecules like that have an internal plane of symmetry, while being a lot more simple, they're achiral for the same reason, is that they have an internal plane of symmetry. All right, so any questions about this here? Probably should do some examples of these, maybe a little bit. See what I got here for you. Any questions on this page here at all? Okay. I do want to point out that you do have a question like this in lab, but that particular question had 5 carbons on it. So you actually end up with a situation where there is no meso version. So what I mean by that is if we had an extra carbon here out on the end, and if you're still at carbons 2 and 3, there would be no meso situation because you have a different carbon count on one side. So they have to be identical down the middle of the molecule. So once again, just to reiterate, I want to go ahead and draw this out. If you actually rotate the bond like this, you can actually get the bromines to be eclipsed to each other. In that situation, the molecule has a plane of symmetry right down the middle. That is achiral. All right. Let's go ahead and switch back over to the PowerPoint. See if I wanted to even go over anything else that's in here. Blah, blah, blah. Yeah, I think we covered a lot of this already. Yeah, here are the example I was giving about stereogenic centers. I think the only last thing I want to talk about in here is optical activity and why we use that terminology. Okay. So it turns out that if a molecule is chiral, we also refer to it as being optically active. So in order to understand what optically active means, we have to look at this picture here. So it turns out that if you have a light from a natural source or from like a light bulb, light is propagating in infinitely many directions, like different waves of light propagation. And here we have a polarizing film, which basically filters out all of them except for one of the waves. And it turns out that if you have this so-called plane polarized light, if your compound, as it's passing, light's passing through your compound, if it's handed, it'll actually churn that light a little bit. So if it churns the light a little bit, we say it's optically active or it's chiral. And this is just how we physically see it. So when we're referring to optically active, we're referring to what we actually physically see in the lab when you run it on a polarimeter. Oh my God, PowerPoint does not like being recorded. It tries to misbehave when I record it. All right, so here's what's happening here is that the sample, so we have the plane polarized light there, it's right after the polarizer, and then it passes your sample, turns the light, and then we see how far it rotated. It is a function of 2 things. One is the path length, like how long is the sample chamber, basically how much space does it have to turn in, and then it also has to do with the concentration of the sample as well. So the more concentrated it is, the more it's going to turn it. We are not going to bother with this calculation though. You can practice if you want, but I'm not going to bother because it's not all that useful for the most part. I do have this funny little picture in here that I wanted to show you guys. If you've ever been to a 3D movie, you guys have had your experience with polarizing film. So what's happening here is that back in the old days when they did 3D movies, you had like the red and blue glasses. And basically what they're doing is they simultaneously send you 2 images at once that are kind of offset a little bit. So like a little bit offset. So then what happens is that each eye is only receiving one of the images because it's being filtered out by light. So like the blue image goes to the left eye, the red image goes to the right eye. The same thing's kind of happening here. So if you look at the polarizing direction on the glasses, they're perpendicular to each other. So when they send the light at you, you're only going to get the opposite ones to your eye. So like one eye is going to get the vertical polarized, the other is going to get the horizontal one. And what happens if you see two images that are slightly offset, and what your brain interprets is 3 dimensions. That's actually why someone who's lost an eye, why they have a problem with depth perception, is because you need the slightly offset image to see in 3 dimensions. And if you ever if you ever hold something close to your eye, you can actually kind of open one eye and close the other eye like that, and it'll appear to be going back and forth. Yeah. And our brains interpret that as being 3-dimensional. So in 3D movie, they're basically tricking your eyes to be 3-dimensional here. And if you haven't done it using 3D with an actual headset, like a VR headset, it's way better than the glasses are. Because my biggest gripe about these polarizing glasses and going to movies is that you only get like 10% of the luminosity to your eye. So it's so much darker than it is like when you actually have it off. I'm not a big fan of 3D movies overall because I think it's poorly done. And then they decided to put it into everything, right? After Avatar came out, they wanted it like in everything. And I think Avatar was like the only good movie in 3D ever made. I haven't seen other good 3D movie, but I remember I saw like a Resident Evil movie. There was like 2 scenes in the whole movie that were actually in 3D. I was like, really? And it was like the starting like credits, and then like there was like one part in the middle, and that was it. I was like, why did I pay extra for this? Anyway, off topic here. Oh, interesting thing too about polarizing light. One more thing about that is you guys probably may have heard of polarized sunglasses. They actually work very good. They work much better than regular ones because you're only getting that one wave of light coming into your eye. And the interesting thing about those glasses, though, is if you actually look at a screen that's polarized, it'll actually look kind of weird to you. Computer screens and like the screens that are like the little things like on a debit machine, like at the gas stations, those are all polarized lights. I know my sunglasses, if I look at it appears to be black when I look at them. Go ahead.
So if you took like 2 polarized sunglasses and turned one around the sideways?
It should be able to block out the light fully. Yeah.
Okay, cool.
Yeah, I remember when I was in graduate school, we had a few assignments where we had to kind of jerry-rig our own instruments together, and this was actually one of them we had to make. We had to make a polarimeter. I actually used a paper towel roll, a flashlight, and 2 polarizing films. That's all it took. And then we fashioned a little sample chamber out of duct tape. It was kind of fun. And it was pretty cool though, because when you hold the polarizing films to each other, one way they would look completely opaque, and then turning just a little bit, you can see right through them both. So yeah, this stuff's pretty cool. I wish we had some film to play with, but we don't. All right, next thing here, and then let me do this last thing here, and then we'll do some examples. So the way we look at E and Z designation in alkenes, we follow the exact same rules that we do for RNS, except now we do it a little bit differently. So what you want to do is you look at the 2 groups that are attached to carbon, and you want to think of them as like separate problems. So like the left carbon, you want to assign a high and a low to the 2 groups, and then the other carbon separately from the first group, you want to assign a high and a low between those. And then you look at where they are relative to each other. And then if you have the case where they are trans, meaning they were opposite, the 2 high groups, that is referred to as E, or trans, and then if they're on the same side, or Z-same side, then we use Z designation. Yep, so I recommend using that. If they're on Z-same side, that means that they're Z. And I do have the actual words here that they're from German words, Zusammen and anyway, they mean like same. They mean like same and opposite, basically. I don't speak German, but I understand they mean same and opposite. So there's my bad German. Sorry about that. All right, so let's go ahead and close PowerPoint. We don't need it anymore. And I think I'm actually going to pause the video.